So now let's continue with the focused ion beam application. So circuit edit and photomask repair. For the circuit edit, for example, if we want this is the circuit. If we want this line to be connected to this line rather than this line, rather than this one. So what we can do? So first, so we can use the mailing. We can use the mailing to remove, to cut off this part. Then we do the ion beam induced separation or electron beam induced separation to deposit a bridge. This way, the circuit here will be connected to here. This is called a circuit edit. So here is another example. In this case, you see there is a break. So the circuit, there is a break. So what you do, you can deposit some metal here to make the connection. In this case, it's done by the focused electron beam induced separation, not ion beam. This is the electron beam induced separation. So we know that for the electron beam induced separation, so the film is not pure with lots of carbon. The conductivity is very low, but it is still conductive for the purpose of the make the electrical conduction. So in this example is the repair of the MR head. In this case, you can see we have this broken. The line here is broken. So this is the coil. This is the copper coil. So the copper coil will give. We have the copper coil. It will generate the magnetic field. So this is used to write the bit. You know, for the magnetic material, so we have the each bit. This magnetic field will be used to write the bit. And this magnetic field generated by this coil. So how to repair this one? How to repair this broken line? So first, we use the selective mailing to remove the cap, the polymer, to remove the polymer cover using xenon difluoride. This xenon difluoride will help the removal of the polymer, but this will not help the removal of the copper, because it will have the copper, and it may form something like this, for instance. CuF2, but this CuF2 is not volatile. It's still solid, not volatile. So as a result, this will not help the removal of the copper, but it will help the removal of the polymer. Then you can deposit some tungsten. So we have the tungsten. It gets connected. Finally, you want to protect it again, but if we don't deposit polymer, so we deposit a silicon oxide layer as the protection layer. But do you remember how to deposit the silicon oxide layer using ion beam or electron beam induced separation? So what we can use two gases. One is the TEOS, because this precursor gas, tetraacyl oxosilicate, oxysilicate. Another one is called the TMAS, is the tetramethyl oxysilicate. So we can use those two precursor gases to deposit silicon oxide. Now here is the deposition parameter for the case of tungsten. This is the deposition parameter. So we have the dwell time, spot time, refresh time, current, and dose and energy. So there is after it is repaired, you can see the signal. So you can see after the repair, the signal is the same as the normal MR head. So that means it is well repaired. So now let's look at what is the MR head. What is the magnetoresistance here? Magnetoresistance. So what is the coil here? So the coil here is for the right. For the right of the bit. So we also need to read the data. So the read is done by the magnetoresistance. So what do we have here? We have the TMR. Now we use TMR. We have the three layers. Yeah, three layers. This is the top layer, bottom layer, again the barrier layer. The top layer, this one is the magnetic. This one is magnetic. This one is the insulator. So here is the insulator. So in the middle part, this one can be typically MgO. So this is insulator. The bottom part is also magnetic. For example, cobalt iron boron. So this is also cobalt iron. This is also cobalt iron boron. But the difference is that the top layer, this one has low corrosivity. So by controlling the material property, this one has low corrosivity. This one has high corrosivity. This one is the insulating. So we have the current pass through here all the way down. We have the current pass. So we have the tunneling. So when we have the insulating layer, so we have the tunneling. So that's why it's called tunneling magnetoresistance. So normally, for example, if the bottom layer is magnetized to the right, The top layer is also magnetized to the right. This way we have the resistance. So we have the tunneling resistance is given by R. So we have the where you go to the medium. So the medium is this is the medium. So we have the top. For example, this is the 0, this is 1. So this is the magnetization. So magnetization up, magnetization down, you have 0 and 1. So this magnetization will flip the top layer. So this one has low coercivity, it will be flipped. So once this one is flipped by the disk, magnetic disk, the base of the disk, it become the top layer, it will magnetize to the left. This is R prime. So the ratio R minus R prime over R. So this can give you 100%. This can be 100%. So R, I think, so when they are parallel, the resistance should be smaller. So this one should be R prime minus R divided by R prime. This can be 100%. This way, by measuring the resistance change, then you can measure whether it is magnetization up or it is magnetization down. So this is the idea of the TMR, tunneling magnetic resistance. But before that, it is called a GMR. But this one maybe you know it. For the GMR, and also this one is the Nobel Prize in physics, maybe 5 or 7 years ago. But now this we use TMR. Let's look at the optical mask repair. You can see this mask has lots of defects. So we have the opaque defect. So here A, E, F, D. So those are opaque defect. We also have clear defect. The clear defect, this one, the chrome is missing here. So this is the chrome. So we know the material is chrome. Here is the glass. So inside here this is the glass. Silicon oxide. So this chrome is here and missing here. So how to repair the defect? So for the clear defect, so we can deposit some carbon. We deposit some carbon here, carbon. So the carbon is opaque. This way we can block the light. This gets repaired. So we can use the hydrocarbon gases to deposit the carbon. For the opaque defects, for example, this part, so we can use the milling. We can use the gallium ion beam mill. So we can use the gallium ion beam to mill away, to remove the material here. Then it can be fixed. But we will see there is lots of troubles. With this milling process. For the case of the phase shift mask, it will be even more difficult to repair because it will remove something. It will remove the chrome. This will cause a phase shift. So now let's look at this one, opaque defect by the gallium ion beam milling. As you can see, it's not hard to remove the material, but the gallium itself. So when you do the gallium milling process, you have the gallium got implanted. This will block. This will reduce the transmission because the gallium is opaque. It will block the light. As you can see here, this is the milling time. This is the ion milling time. So even though it may go very, very long time, for the casing of visible light, you get 70% transmission. For the casing of 254 nanometer, you get only 20 nanometer transmission. So today we have 193 nanometer. So here you see the transmission may be also at 20%. So because of the gallium, this is a big problem for the mask repair. So here's the example. So here you have this part, you have the radial defect. After repair, you see it is removed, but still there is some gallium inside. So after the exposure, you have this chunk here. This part is not supposed to be here. So how to solve this problem? There are 3 ways to solve this problem. 1, 2, 3. The first one to solve this problem, we use RE to etch away the glass. For example, so here we have this is the glass, but we have a lot of gallium. We have a lot of gallium inside the glass. So what do we do? We have a lot of gallium inside. So what do we do? So first we etch away. So we use the fluorine gas. So we use fluorine gas to etch to etch away some of the glass. Then this gallium will appear on the top surface. It will be on the top surface. Then we can use wet etching using some acid to remove the gallium. Then we can continue. We can etch again. We etch again. We can continue. Repeat. We etch again. Then we use the wet etch to remove the gallium. So as you can see here, for 255 nanometer wavelengths, so after repair we get a 20% transmission. After 30-second etching, 30-second RE followed by wet etching, we get 60%. So after another, this one is 30-second etching, wet etching, 50-second RE wet etching, we get 90%. If we do one more time, 30-second dry etching, wet etching, then 30-second dry etching, wet etching, then 30-second, 15-second dry etching, wet etching, we get almost 100%. This is one way to repair the mask. So basically, we remove the glass to expose the gallium, then it can be removed. The second one is called bias repair. This one is obviously the easiest one. So what you do the over etch. You do the over etch beyond the defect area. You can see you over etch beyond the defect area to compensate the light blocked by the gallium. You can see it gets better result. The third method is called we use electron beam. We know that normally electron beam cannot remove the chromium. Electron is too light to remove any material. But if we add these two gases in the chamber using the gas injection system, then it will form a chrome oxygen O2 Cl2. So this one is volatile. Then effectively we can use electron beam with this gas to etch away the chrome. So now I want to ask you one question: how to RE chrome? How to plasma etch chrome? So what gas can be used to etch away the chrome? So from here you can see we can use the chlorine. We can use chlorine and oxygen gas to etch away the chrome in the RE process. Now let's look at two more applications: superconducting and nanopore. In this example, so we use the WCO. So we deposit tungsten using WCO6 gas. As we know, there will be a lot of contaminants. So we have 40% carbon, 40% tungsten, we have 20% gallium. So this material is not very pure. So this is the wear. But this material that is not pure, it turned out this one to be a very good superconducting material. You can see here the transition temperature. So the transition, this is called the TC. So the transition temperature, or critical temperature is 5 Kelvin. So for comparison, for the single crystal pure tungsten, the TC is only 0.01 Kelvin. So that means this material, even though it is not very pure, it is better a superconducting property than pure tungsten. It is not so surprised. For example, we know like silver or gold. Those metals, they are very good conductor at the room temperature, but they are very, very poor superconductor. You need extremely low temperature to make them superconducting. So on the other hand, some other materials like this one, this is called YBCO. This is the this is 2 BA3. This was 7. Close to 7 minus sigma. So 1, 2, 3. This one is the first, most important superconducting material that has critical temperature beyond the liquid nitrogen temperature. So this is very good. So the critical transition temperature is beyond, it's higher than liquid nitrogen temperature, which is 77 Kelvin. But you can imagine this is oxide. Lots of oxygen. This one is a poor conductor at the room temperature, but it is a good superconductor. So here the same thing. So poor conductor here, but it's better superconductor than the pure tungsten. The next example is the nanopore. So you can imagine. So this one is the biological nanopore. It comes from the cell, the membrane of the cell. You can imagine when this pore is open, so if you apply a voltage, you have a liquid, you apply a voltage, then the current can flow. So the current so the current can flow. So this is the measured current can flow easily. But when you have the DNA inside, so then it will be blocked. The current will be lower. This way you can do the DNA sequencing. You can do the DNA sequencing. You can also separation of single-strand DNA and the double-strand DNA and determine the DNA chain length. But this is why, this is the cell membrane is it's a polymer, very hard to manipulate, very hard to control. So what you can do, we can make synthetic channel. That means we make the pore by the nanofabrication method. Then you measure the current, you measure the DNA property. So how to make the synthetic nanopore? So one way to do this is to follow this procedure. So we have the silicon wafer. So first, we deposit the low-stress silicon nitride by the low-pressure chemical vapor deposition. Then we do the photolithography. We activate the nitride. Then we do the QH etching. Finally, we get this very thin membrane. This thin membrane, we can use focused ion beam to drill a hole. So when you use a focused ion beam, you can drill a hole about maybe 5 nanometer. But this is still too big. This is 5 nanometer hole is still too big for the casing of the DNA, because we know the DNA is about 2 nanometer. So how to drill a hole that is 2 or 3 nanometer? This is done actually nowadays. Another method called they use the TM. So we use transmission electron microscope. We use electron beam to drill a hole. So you may wonder how come electron beam can drill a hole. So actually, when we have the ion beam, so we sponsor away. We sponsor away the material when we have the ion beam. So when we have electron beam, we cannot sponsor away the material, but we can cause the material to migrate. We can cause the atom to migrate. So eventually, if the atom, here the membrane, you have electron come in. If the atom they move around, they move away. If the atom they move away, then there will be a pore here. So this way you get, because TM, is very high resolution, very, very finely focused electron beam with the diameter angstrom. So you can have 1 or 2 nanometer pore by the TM milling. This one is very, very slow, but you just need to make 1 pore, so this is not a good problem. So this is the topic, this is the focus of the company called Oxford Nanopore. It's called Oxford Nanopore. Obviously, this company is a UK. This is a UK company in Oxford. So what do they do? So they use the DNA. They use the DNA to do the. They use the DNA to sequence. They use the nanopore. They use the nanopore to do the DNA sequencing. So nowadays, so what is the main problem for this technology? So one problem is that the DNA passes through too fast. So DNA they pass through very, very fast. So the focus is how to slow down the DNA. If you can slow down the DNA, then you can do the sequencing. Otherwise, if it passes too fast, each of the base pair. So we have the AGCT. If each of the base pair passes too fast, then it's hard to resolve it. So you have to slow down the transport of the DNA through the nanopore. So this is one of the focus for the current research. So the eventual goal for this work is to make a $1,000 human genome. So in the future, maybe in 5 or 10 years, if you want to know your genome information, you can spend $1,000 to get the genome information. So this is the ultimate goal of this kind of product. So now let's look at proton beam rating. The proton beam is nothing but hydrogen ion. So we will first talk about hydrogen ion, then we talk about a helium ion. For the casing of the proton beam, first, the proton beam is heavier than the electron beam. So how much heavier? It is almost 2,000 times. We know the proton, the mass of the proton is almost 2,000 times that of the mass of the electron. So when it is heavier, it will not backscattering, not too much, not long-range backscattering. So we have smaller proximity effect. Because this one comes from the linear accelerator, so the energy is very high. normally the energy is 0.5 to 2 mega electron volt. For the case of electron beam, we use tens of kilo electron volt, but here the proton beam we use mega electron volt. Because it had very high energy, it can penetrate very, very deep. You can see 60 micrometer without much lateral scattering. But for the case of electron, you get a lot of lateral scattering. This is why it's 50 kilo electron volt electron. This is 2 mega electron volt a proton. For the case of 50 kilo electron volt gallium ion, it goes about 50 nanometer. But this one is 50 nanometer. This one is about 30 micrometer. This is 60 micrometer. Then because of this trajectory, it is very good for the fabrication of the high aspect ratio structures. It's very good for the high aspect ratio structure fabrication. Another way to do this, we know accurate lithography. Accurate lithography can also give you very high aspect ratio structures. But for the accurate lithography, when you have the high aspect ratio, you need to have very deep you need a gold mask. You need a gold mask, which limits the resolution because it is difficult to have the gold mask with very tall and narrow structures. But here is the direct writing. We can have nanometer scale resolution with high aspect ratio. So here is the facility from Singapore, from this place. So this way you can see first, so we have this proton accelerator. But this is not something normal. The accelerator like a synchrotron radiation is also an accelerator. But this one is usually a big facility, a very, very big facility. In fact, in the world, only 3 places do the proton beam lithography. This one, Singapore. There is another Japanese facility that can do the same thing. Then there is the Swedish lab. They can also do the proton beam lithography. So you have the accelerator, very, very large facility. Then you use the magnetic lens to focus the proton beam. You may wonder, we have seen that for the case of the gallium, we use electrostatic lens to focus gallium. We cannot use magnetic lens to focus gallium because the Lorentz force, is given by EV. This is Lorentz force. You can see for the case of gallium, the speed is very low. When you have very slow speed, you need a magnetic field extremely high, so which is not very available. But here for the case of the proton, the proton beam is 60 times. The proton beam is 60 times lighter than gallium ion beam. So we have lighter ion beam for the same energy, you get higher speed. Secondly, the proton beam has very high energy, so we have we have 2 mega electron volt. For 2 mega electron volt versus 30 kilo electron volt, we have very high energy. This also gives you very high speed. We have very high enough speed. You can use the magnetic lens. To still have the high enough Lorentz force. So this is the setup. Now let's look at the interaction of the proton beam with the material, with the resistant material. So first, for most of the parts, the interaction with the electron, is much higher than the interaction with the nuclear. This is the proton beam. There will be a lot of interaction with the electron because electron is very light, so electron can follow the proton beam. But for the nuclear is heavy. So the nuclear cannot follow the fast moving hydrogen atom. So there will be lots of collision with the electron. But because of the high mass mismatch, as we know, the proton beam is 2,000 times heavier than electron beam. So the proton-electron collision do not significantly deviate the process trajectory. I will need thousands of collisions in order to slow down the proton. When the proton becomes slow, the nuclear can follow it. There will be a lot of nuclear collision when it becomes slowed down. Then there will be beam broadening. As you can see here, most of the paths very high, very collimated, not much deviation. But near the very end, we have a lot of collision with the nuclear. Then you get snubbed and you get broadened a little bit near the very end. So we know that for the proton beam, this is like similar to the gallium ion beam. It can generate secondary electrons. So those secondary electrons can expose the resist, just like the electron beam lithography. So here are some examples. This one is the PMA structure. This is the high aspect ratio structure in SU8. So we know that SU8 is chemically amplified resist. It has very high sensitivity but very low resolution. But in this case, we get 60 nanometer resolution. We get high resolution because here the pattern is very sparse, not very dense. When you have isolated lines, you get very narrow lines. This one is HQ. This is HQ. We know this gave the record resolution for the electron beam lithography because this one is more stable than the polymer resist. This one is 22 nanometer resolution. So the proton beam exposure of the resist is about 50 times more sensitive than the electron beam exposure. This is similar to the gallium. So we know that for the casing of the gallium, the exposure of those resist by gallium is 100 times less of the 100 times higher sensitivity than electron. The proton also has much higher sensitivity than electron beam lithography. But the current, the current is much lower than the electron beam. So we can play with the energy of the proton beam. But when we have the low energy, this is not very low actually, 500 kilo electron volt, it can penetrate to these depths. When we have 2 mega electron volt, it can penetrate to these depths. As a result, we use high energy here, low energy here, we can get this Stonehenge structure. This is the historical. This is like a sightseeing point in the UK. Maybe 2 hours from London. So again, the resist here is SU8 resist. Can we do the same thing? So this is a negative resist. Can we do the same thing for the positive resist? If we have the positive resist like the PMA, what will happen? What will happen with the positive resist? So when you have the low energy exposure, maybe you expose here. Low energy you expose here. We have high energy you expose to here. This is why it's high energy. This is low energy. In the end, after development, you get something like this. After development, you get something like this. So you cannot get a structure like this using positive resist. You can only do this using the negative resist. So now let's look at next one is the helium ion microscope. A helium scanning helium ion microscope. This one has very high resolution. It can get resolution at 0.24 nanometer. So how to do this? So what do we do? So we have something. We have a very sharp edge. And then we have the helium here. Helium ion. So we move the helium ion from the left to the right. So when the helium ion hits this surface, you get the high signal. When the helium ion comes here, you get a low signal. So when the helium ion move across the edge, move across the gas, you get the transition. You get transition like this. So the width here, the transition width, this one is 0.24 nanometer. So this is actually the beam size of the helium. It can give you a very, very good resolution. So for the case of helium, it's too light for the ion beam, so it's mainly used for the imaging purpose. For the imaging, we compare it with the SEM. So we compare this one with SEM. So first, so the helium atomic number is 2, the mass is 4, we have 2 protons and 2 neutrons. So the mass will be 8,000 times that of electron. You get shorter wavelengths, you get less diffraction. So the interaction volume, is also smaller. This will also give you higher resolution. So the material contrast is different from SEM. We have different material contrast, like the gallium ion beam. And the next, so the helium ion can produce more secondary electrons than electrons. So one helium ion can produce 3 to 9 secondary electrons. So one electron comes in, it produces only 1 secondary electron. As a result, we can use lower current we can use very small current to still give you enough signal for the imaging purpose. When you have a lower current, smaller current, you need a smaller aperture. That means smaller beam converted angle alpha to smaller beam size because of the less chromatic and spherical aberration. But this small current also gives you smaller charging effect. And lastly, this is also good for the insulating material. So lastly, it has higher penetration depth, higher depth of focus. So this one shows the diffraction effect. You can see, so longer wavelengths, more diffraction, shorter wavelengths, smaller diffraction. This for the imaging. We use a helium ion microscope is mainly used for the imaging purpose, but it can be used for the milling purpose. So when we do the milling, we compare with the gallium ion. So first, helium ion is much lighter, so there will be less damage than the gallium ion. There is no staining because helium ion will not block the light, but gallium ion will block the light. That is, the helium implantation does not occur too much, but gallium will create a lot of defect. So at a very high dose, it will form the bubble. It will form the helium bubble. You have the sample here. Of this silicon here, you have helium ion to mingle with. You try to mingle with the silicon material. Then there will be the bubble. So the helium bubble will be formed. So when the helium bubble is formed, the silicon actually can become protruded. So that means we have the helium to mingle with the silicon at the beginning. It becomes taller. But if you keep milling, eventually you can still mill a deep hole. So if you have a longer time, eventually you can still mill a deep hole. But at the very beginning, you get a bump first. So because the helium is very light, so the sputtering yield is very low. It's about 100 times. So 100 times slower than the gallium ion. So you can use it to mingle with the material, but it's very slow. 100 times slower sputtering yield than the gallium. If we add some gases like xenon difluoride, this will help. In principle, we can also use the helium ion microscope to do the material deposition. But in reality, I have never seen people use this one for the material deposition. It's mainly used for the imaging purpose, and some people also use it for the milling purpose. So now let's look at how to generate a helium ion. This one is actually this source. So we have talked about there are 4 ion sources. So this one we haven't talked about this because field ionization source. This one is actually used for the helium ion. So this helium ion uses the field ionization source. We need a very high field. This is actually studied earlier than the liquid metal ion source. But until this company is called Alice, this company they make very reliable and stable helium ion source. Then it becomes possible to use the helium ion for the microscope application. First, we need very high field, like a cold field emission. We need very high field. This one it looks like blunt, but actually this should be extremely sharp. This one should be very, very sharp, but here it doesn't look so sharp. You have very high field. Then you have the helium ion. This is the helium gas. So when the helium gas comes close to the atom, this one is tungsten. The material here, those are tungsten atom. When the helium comes close to the tungsten atom will take away one electron, so the helium will be ionized. Once they are ionized, it will be pushed away by the very high field. It pushed away to form the ion, to form the helium ion. So from here you can see that this is a kind of atomic interaction. This is an atomic interaction. So when the helium only comes to this atom or this particular atom or this atom, they can recognize each of the atom. Then it will be ionized to form the helium ion. So the helium ion current can be controlled by a pressure. So higher pressure give you higher current. So for the lifetime, so this can last about 1,000 hours. This is about 1,000 hours. It's 40 days, but actually, it's normally you need to redo it after less than 20 days. But here it said 40 days. So what happened? So the gas molecule, like helium or other gases, oxygen or nitrogen, they cannot come to the surface because when they come here, they will be ionized. Then they are pushed away. So those gases will not attack the surface because they will be ionized before they can collide with the surface. So the electrons can be pushed to the surface, but the electron will not damage the tungsten tip. That's why it can last for 1,000 hours. This is a pretty long time. Looks like a very long time, but we know that for the Schottky emission, for the SEM, for the field emission SEM, this one can last 2 years. For the SEM, the gun can last 2 years, but this one is only 40 days. It's still much shorter time than the electron microscope. So actually the sound is very sharp. So how sharp it is? So you can imagine. So the sharpest emission source is the single atom emitter. For the casing of helium ion, we have single atom emitter. So what do we do? So for example, this is the tungsten. It's not so sharp. We have a lot of atoms. It's not very sharp. This is called source blunting. It is blunted. It becomes blunt. So what do? We apply a high voltage, like 45 electron volts, 45 kilo electron volt. Then the tungsten atom will be pushed out. This is called field evaporation. So we have 45 kilo electron volts, so tungsten atom will be pulled out. So one of them, they will be pulled out one by one. So eventually, after some time, you get this image. This is called a tremor. It's called a tremor. Tremor means at the very end, there are only three atoms at the very end. So once you get this tremor, you lower the voltage. So here it's 45 keV. So when you get this tremor, you lower to 35 keV. So this is the operation voltage for the helium ion. Then you keep this one, you maintain it at a low temperature, cryo temperature, and also very high vacuum. But here you have three emitters, you have three atoms. So what you do, you rotate the source a little bit so that only the emission from one of the atom can pass through this aperture for the ion microscope. That's why I said this is like a single atom emitter. So we pick only one of the atoms as the emission source. So the size of the source is less than 1 angstrom. This gives you a very bright beam. So now how to get this kind of image? So how to get this kind of image? This one is called field ion microscope. It's called field ion microscope. So what do? You have the sharp tip, you have very sharp tip, you apply a very high voltage, this one, high voltage, 45 kilo electron volt. You have the gas molecules, you have gas helium or neon. Then there will be, the gas molecule will be ionized, it will be emitted from the tip. This part is called scintillator. So this one is sensitive to the light, sensitive to the ions. So when the ion bombards the surface, it will emit the light, it will glow, emit the light. You get something like this. So each of them is actually one atom. The first work of this kind of work is done by this one, the Irving Uller. So I think he is a very great physicist, but somehow he didn't win the Nobel Prize. So he and his student, they saw that they have this image in 1951. But this is the first time that human being see a single atom in 1951. So this is the setup he used. This one, they had very high vacuum here, but looks like this one has cooling, but here looks like they are not cooled. You can imagine, this is the story, it says this is atom, but this article was written in 1955, but actually they see this atom in 1951. You can imagine he must be very excited. He must be very excited to be the first human being let's see the item. His student 这个 Indian Indian his student Indian and he himself they are the first two people to see the item for the human being. So what is good? Sorry, this is the field eye microscope. But today this one is further developed. It become called item probe. But this item probe can tell you not only the arrangement of the item, but also what item you can have. For example, this item may be tungsten, this one may be gold, this item may be silver, this item may be carbon. So this is called item probe. So in Canada, we know that the McMaster University, they have the best electron microscope and ion microscope. So we talked about a polymer ion source. Oh, you can answer it. For the polymer ion source, this place has the polymer ion source, and also they have this item probe. So here's how these things work. So first, you prepare the sample. So to prepare the sample, you need something sharp. So this one can be done by the focused ion beam. So we can use the annular medium. You remove the material around, you leave behind the material at the bezel. So this way you get very sharp. Then you can do this setup. This is the field ion microscope, but this one used to field ion microscope. But the purpose for this one is not microscopy, but usually to study the material property of this tip. You have the emission here. In this case, they also shine the UV light. I think the UV light will help the emission of the items. Items will come to the screen. Where the time of flight. So you can imagine the heavier the item, the longer the time to take. So the heavier item, longer time. So by using the time of flight, we can tell what item we can have. For example, in this case, we can see. Then finally, you do the model. You can do the item by item model. You can build out the tip. You can build out the material composition of the tip. For example, this part may be tungsten. This part may be silicon or other materials. So you can imagine this is really extremely good calculation tool. You can do the 3D item by item model, item by item measurement of the material. This is really no other method can do this kind of measurement. So I once went to McMaster University to listen to the talk about this item probe. So they said they have analyzed a billion or how many billion items by using this technique. So now let's look at the imaging by the helium ion microscope. Now this one I get it from the internet. This is the report by one of the students. Look, this is what he said. He said the Scania helium ion microscope is usually a serious and major breakthrough in seeing things. So the application is usually a mass. So this is microscope with the resolution close to the TM. Do not need sample preparation. So we know that for the TM, it takes at least 5 hours to prepare the sample by the focused ion beam or by other method. You need a very thin sample for the TM. But here, there is no sample preparation. This is the scanning mode, not the transmission mode. So the voltage and the material contrast is better than ICM, and also less interaction volume give you higher resolution. You can see you get much higher resolution. So this is one example here. You have this one is the solder bump. This is the helium ion microscope. You see the different material contrast. This one on the right side is the ICM image. So you see less contrast. So here is another example. In this case, you can see the material. This is the helium ion microscope. So now you can see the material inside is different from the material outside. Some of the material here it got bombarded away to here and to here, we get different contrast. For the same material, we do the SEM imaging. You can see you cannot tell the difference between the material inside and the material outside. So this one is the isolator. So because we know that for the helium ion microscope, we have higher yield of the secondary electrons. As a result, we can use lower beam current to have a signal. When we have lower beam current, we have smaller charging effect. So we can do the imaging of the insulating materials. So this is really good. But there's so what's the main problem? At the University of Waterloo, we have one. So we have this one at the University of Waterloo. There are maybe 3 or 4 of them in Canada. 3 or 4 helium ion microscopes in Canada. So one in Waterloo, another one in Alberta, another one in a company in Ottawa. Maybe there are maybe 2 more others. But actually, this one is not very heavily used. So most of the time of the year, this machine is idle. Nobody uses it. This is obviously a very big waste of the money to buy this equipment. This one may cost maybe $2 million, but actually nobody uses it. Very few people use it. So the problem is here. So the lifetime is 1 summer hours. So in reality, every 2 weeks we need to make this trimmer. To make this trimmer take about half a day. This is not a big deal. Half a day is not a big problem. But another problem is the resolution. The resolution we can get here, we know about 0.3 nanometer. This is very good resolution, but still it is not like an angstrom. For the TEM, so when we need atomic resolution, we go to the TEM. The TEM can see atom by atom, but helium ion microscope cannot see atom, so this is not very good. When we have 5 nanometer, when we need for 5 nanometer, people use SEM. So SEM is about the cost, the user fee for the SEM is 1/3 the user fee of this helium ion microscope. So normally for the larger feature size, people use SEM. Bigger than 5 nanometer, people use SEM. This works well. If we want higher resolution, atom resolution, people use TEM. So only between atom and 5 nanometer, maybe 1 to 5 nanometer, the helium ion microscope is good. So obviously it has better material contrast, but in reality, as I said, because this is a high cost, so this is not, unfortunately, we have this fancy machine, but not many people use it. It is idle most of the time of the year. Thank you.